Hello, welcome to this short video about Newton's three laws of motion. Newton is indeed the giant whose shoulder we all stand upon, especially when we're talking about forces and motion. Much of this whole topic is based on Newton's three laws of motion, which were first identified in his, seminal piece of writing, the Philosophiae Naturalis Principia Mathematica, often just known now as the Principia. It is the principle of many and all of our simple understanding about forces and motion. And in this video I'm going to explain the crucial three laws of motion which he identified. Newton's first law. Bodies will continue to move with a uniform velocity, which we must remember includes being stationary unless acted on by a resultant force. So what we're going to think about here is, this means if a body changes speed or direction, a resultant force must be acting on it in some way. Here's a classic example of that. So here we have a man driving along, and what happens is that when the car hits the wall, the man continues to progress at exactly the same motion because he was not wearing a seatbelt, and therefore the resultant force has not acted upon him, causing him to come to a halt. So he continues on in the same direction with the same motion because there's no force acting upon him. Balance forces also describe what's known as static equilibrium. So Newton's first law recognizes that if all the forces are balanced and the resultant force is zero, that means an object will stay in static equilibrium, so not moving. The examples you can see in front of you are the thought of balls floating. Now, each one of these has a different density, and therefore the various forces upthrust due to buoyancy are different for each one of these balls. But what we find is they've reached a static equilibrium, a place where they're no longer moving because the forces are balanced, and therefore there'll be no associated acceleration. They will maintain a constant velocity, which in this case is zero. Next, we think about Newton's second law of motion. This is really one which we apply some numbers to. So Newton's second law of motion tells us that the amount of acceleration that a force produces depends on the mass of the object being accelerated. And this is normally remembered as the formula F for the net force equals mass times acceleration. So let's consider a mass of car 1,000 kilograms. Can you work out the acceleration undergone by this car in these three situations? Pause for a moment and make the calculations you need, and then we'll check. Hopefully for the first car you reckon that the resultant force is 500 newtons, and therefore the acceleration is going to be 0.5 meters per second squared. For the second car, you should have recognised that although there's 500 newtons thrust, there's 100 newtons, we'll call it air resistance. It's not featured here. And so that means overall there's a resultant force of 400 newtons, and that will give us an acceleration of 0.4 meters per second squared. Our final car appears to have reached its terminal velocity. The thrust is 500 newtons, but the frictional forces are 500 newtons in the opposite direction. So the resultant force is zero, which tells us that the acceleration is 0 meters per second squared. Now remember, just because the acceleration is zero, it doesn't mean that the car is travelling or is stationary. It can be travelling at a constant speed. Newton's third law, the action-reaction law. Whenever one body exerts a force on a second body, the second body exerts an equal but opposite force on the first body. This is actually the law which most people often get confused about. And I'll explain some of those features in a moment or so. First of all, let's think about the force applied if you were a boxer. If you just happen to be a bare-knuckle boxer, now you have to remember that if you apply a punch, you will apply a force onto the other person. But exactly at the same time, when you apply that punch, what will happen is there'll be an equal and opposite force being applied to your hand as well. Just remember, if ever you punch a wall, your hand gets hurt as well. And that's because of Newton's third law. There's an equal and opposite force. The opposite is identified by the negative feature on the F subscript BA. And that's how it's shown mathematically. Now, as I said, this is often one which people get confused over. The essence is, for every force there's an action, there's also a reaction. Here are some examples of actions and reactions. Now, please note that in every situation, the forces are acting on different objects. What we have is the first one with the car. We have the frictional force of the car on the road, and then the frictional force of the road on the car. With the space shuttle, what we can see is we have the gravitational attraction of the space shuttle to the planet Earth, but simultaneously we also have the gravitational attraction of planet Earth to the space shuttle, or vice versa. With the man pushing the fridge, we have a force which is being applied onto the fridge, and vice versa, we have a force of the fridge being applied onto the man. Because they're being applied to different objects, it means they don't just automatically cancel out. And people often get into that trick. You've got to remember that it's being applied to a different object. So, these are not action-reaction examples. So we have the weight pushing down and the normal force pushing up. Now the key thing here is that what we're talking about are two forces on the same body. That means it's definitely not an action-reaction. And also we have two different types of forces, which is another indicator that it is not an action-reaction pairing, what's known as Newton's pairs. So please be very aware of that. And also the key thing is the action and reaction have to be working in opposite directions to each other. So just to recap, Newton's three laws of motion. Newton's first law, bodies will continue moving with a uniform velocity unless acted on by a resultant force. Okay. So that means that if a body changes speed or direction, so if it's going around a corner and it's changing direction, a resultant force must be acting on it. And that's what you've got to remember. Newton's second law normally comes down to the basis of Newton's equation, force equals mass times acceleration. Officially, the resultant force is equal to the rate of change in momentum. And we'll talk about this momentum definition in a few lessons' time. And Newton's third law is every force has an equal and opposite force acting on another object.